Well, I'll just start talking. So my name is Carl Steinbach. I'm the tech lead for the Hadoop development team at LinkedIn. It's a group of about 20 people responsible for making the Hadoop platform at LinkedIn work better, making people more productive on it. And then to do that, we contribute to a variety of upstream projects. We also work on a variety of internal projects. And one of those projects is the main topic of this talk. So before I start talking about that project, I want to just quickly talk a little bit about the scale of Hadoop at LinkedIn. So LinkedIn started using Hadoop back in 2008, very early adopter of this system. At the time, there were no books on Hadoop, there were no user groups. Really the only folks out there who were using it were Yahoo and a handful really of other companies. And the first cluster, was just 20 nodes. It supported 10 users, 10 production workflows, including the most important workflow at the time, which was PYMK, or People You May Know, which is popularly regarded as sort of the engine of LinkedIn's growth, especially in the early years. And in terms of what people were running on the cluster, it was mainly MapReduce and Pig. LinkedIn inherited a lot of people from Yahoo's Hadoop team, and that helps to explain, I think, why Pig was sort of one of the early components brought in and why it remains popular today. So here we are now roughly 8 years later. Hadoop just celebrated its 10th anniversary. At LinkedIn, the scale has grown quite a bit. So we now have over 10 clusters. We have over 10,000 nodes in total. Our largest cluster has over 3,500 nodes without federation. We have over 1,000 users using the platform on a weekly basis. And I think that's one of the most interesting things about LinkedIn, really the diversity of the people using the platform and also the diversity of the things that they're trying to accomplish on it. In terms of what they're doing, we have hundreds of production workflows that run every day, thousands of development and ad hoc queries that people run, and the components have diversified quite a bit as well. So I think that since Hadoop arrived at such an early point and in sort of a very informal manner, people at LinkedIn continue to enjoy sort of an unparalleled level of freedom in terms of what they're allowed to run on the cluster. If you want to write your own framework, go for it. That's the general advice, although maybe I wouldn't give people that advice necessarily. I would recommend, look to see if there's something that already exists out there that can satisfy your use case. But, in general, I mean, people definitely find a lot of problems that are not adequately addressed by existing components, and to solve those problems, they've written some interesting stuff on their own. So in addition to MapReduce, Pig, and Hive, we have a component called Goblin, which is a universal ingest framework for Hadoop. Qbert, which is like a cubing, slicing, and dicing engine for optimized joins and rollups. We started using Scalding. Spark is, of course, a big thing now, and Presto as well. So, what did we learn along the way? Well, one thing that we sort of learned from first-hand experience is that scaling the hardware infrastructure is a challenge. I gave a talk yesterday about some problems we ran into, growing a cluster to more than 3,000 nodes, and we've spent significant time addressing those problems and coming up with some nice solutions to sort of streamline that process. My slides from yesterday are posted online. If you weren't able to attend that talk and you're sort of interested in this topic, I'd recommend taking a look at those. Also, Chris Narath from Hortonworks gave a great talk yesterday on a related topic, HDFS scaling, and the problem basically with scale testing Hadoop, and pointed out some of the bugs in particular that have gone in upstream that have caused lots of problems. So I'd recommend checking out that presentation as well. So as hard as scaling hardware infrastructure is, I think the thing I've learned is that it's actually a lot harder to scale the human infrastructure. And for me personally, I think that's one of the more interesting aspects of this, that there's almost sociology at play here. How do you get 1,000 people who are interconnected with each other in some ways that are visible as well as invisible to communicate effectively with each other, to work together effectively, and to sort of manage change on a constant basis? And that's really, I think, what this project Dali is about. So I should probably stop and explain that the name started out as data access at LinkedIn. Over time, it's just sort of morphed into the name, right? I no longer capitalize the letters, I guess sort of as a branding move. But the motivations really behind Dali stem from sort of three distinct groups of people at LinkedIn. So on one side, you have data consumers. These people are trying to extract meaning from all the data that every click on the website generates. And before they can do that, they have to answer some really basic questions. Where is the data that I'm interested in located? Who produces it? Which is a harder problem to answer in many cases than it should be. As soon as they answer that, the next question is, where is the data located? And once you get that question answered, you need to know more details about sort of the physical aspects of the data. How is it partitioned, organized into directories and things like that? And what format is the data stored in? And if you look at a typical pig script or a MapReduce script, there's often this boilerplate logic at the beginning, these incantations about, well, here's where the data is located, this is the schema that I'm going to associate with the data, and that's repeated in every single script. That represents technical debt, really, right? It represents inertia, makes it very hard to then change the schema to evolve it subsequently because we're going to break all of these scripts. And it also introduces the chance that people are going to make subtle errors. On the other side of the business, you have the data producers. And I think at LinkedIn, one thing that's sort of evolved over time is that data infrastructure is really divided into the online side and the offline side. The offline side you could think of as like primarily Hadoop, but OLAP analytic style systems. And on the online side, you have a lot of transaction processing systems, site serving systems. And every time something happens on the site, it generates an event. And this gets published to Kafka. It sort of traverses over the wire, and eventually it ends up on the online side. Most of the people, though, who own these online services have only a vague notion of who is consuming the data that they're producing. And that can cause some real problems. So for one thing, you have really no idea who depends on your data, which makes it very risky to make any changes to the data that you're producing. You don't know what aspects of the data people are depending on, whether if you evolve the schema in a manner, if it's going to break a bunch of people. And frequently when you do that and you break people, you only find out about it maybe a week later, after those people on the online side have traced back the series of jobs, the pipelines, to figure out who broke them in the first place. And because of that risk, we see other problems. People are reluctant to make changes because once you make a change, you really can't take it back. There's no distinction between a public and a private API for these events. So if you add a new field and you decide a week later, well, that was a mistake, or I wish I had named it something else, or the type should have been something else, well, you're kind of screwed at that point. And we see a lot of schemas that have 100 or 200 fields in them, and maybe 50% of them are just deprecated. They're no longer really used. And that causes a lot of problems for data consumers. How are they supposed to distinguish between deprecated and live fields? And the best way right now available to people to communicate these details are schemas. So a couple of years ago, LinkedIn standardized on Avro as a data serialization format. And I think that was a really good choice at the time. You're able to sort of solve format incompatibility issues by just saying, look, we use Avro everywhere. And Avro has a lot of nice features, chief among them the fact that the schema travels with the data, so it's a self-describing format. But the schemas that Avro provides are basically physical schemas, right? So you can say that something is an int or a big int. You can say that something is a string. You can't, though, say, well, actually, this string is a URI. And in a lot of cases, things like that would be particularly useful. So I think one thing that's interesting here is that when you see a situation like this, two camps of people who are running into lots of problems, it's oftentimes because a third camp of people are dropping the ball. They're being fundamentally really lazy. They're trying to take it easy. And in a way, I wish I could say that was the case here because it would be an easier problem to solve. The fact of the matter, though, is that this problem that affects the online and offline sides of the business actually makes life really bad for the infrastructure providers. People on my team as well as other teams within the department that I work. There are a lot of things that we would like to do to make the platform run more efficiently. We'd like to convert to a different storage format. I'm sure a lot of you have heard of new columnar formats like Parquet and ORC. And our hands right now are tied. We can't do that because there are thousands of workflows out there that basically make this assumption that the data is stored in Avro. Similarly, we would like to be able to repartition some of this data. When you're talking about data-intensive computing, the single biggest optimization that you can do is getting clever about what data you don't have to read. And a straightforward way of doing that is figuring out what kinds of filters people are executing typically on data, and then arranging your data set in a manner where you can easily just eliminate large portions of it from your scan by correlating it with the filter. Right now, we date partition everything, which is good because a lot of things are actually filtered on date. But then there are some other data sets where it would make a lot more sense to filter or partition based on event type, or perhaps user ID or things like that. And right now, that's out of reach to us. Another issue that's sort of on the horizon is that the size of the data at LinkedIn is growing faster than our ability to build clusters large enough to hold it. So, I think the situation is not that great for people right now. They have to manage a lot of details. And my concern is that a year and a half from now, there's going to be one more big detail that they're going to have to manage. And that is that we'll see workflows where the workflow needs to consume data, and there's not any one cluster where all of that data is located. So now you have to worry about coordinating your workflow across multiple clusters. And as soon as you do that, then I have one additional thing that I can't do. I can't move data from one cluster to another because now I have a bunch of workflows that depend on it being on this specific cluster. So with that sort of like existential threat looming, we've been working on this project called Dali. So, this is just a nice picture that kind of, I guess in a way, conveys the chaos right now that we have in the system. There's a tight web, really, of dependencies, of obligations that exist between people. No one really knows what those connections are. No one has a global view of them. And we only find out about these connections frequently when things break. And that's not the ideal time to figure that stuff out. So the goals really with Dali are to make the analytics infrastructure invisible so that people don't have to worry about it and so that they can focus on the job that they're trying to get done, analyzing data, producing data, and managing those relationships. And the project is sort of broader than what I'm going to talk about today. Just to quickly sort of cover the broader vision, we want to take the file system that HDFS provides and be able to provide one global namespace across multiple HDFS file systems. We want to move from basically a file system API to a dataset API. We want to provide views layered on top of this dataset API, which allow people really to better manage the contracts that exist between producers and consumers. We want to make things easy to discover and manage by providing fine-grained lineage, linking these things together. So I think it helps with projects often to sort of establish what the major themes are. And I've tried to do that with folks on my team. And I think one good theme that we've been working with is that it's important to separate logical and physical concerns. That as soon as you start to expose physical details to the people running on your platform, you've really worked yourself into a corner, and you've also made lives harder for them. I think another major theme is that GUIDs, globally unique IDs for logical entities, are a great thing. Every entity deserves a GUID. GUIDs are cheap, and they make life better for everyone. But these entities do change over time, so a GUID alone is not enough. And we also want to be able to version these entities so that people are able to say, hey, I want to refer to this specific thing at a point in time, and I know that, well, perhaps the name is the same, but these two different snapshots represent two different versions of that entity. Another sort of animating theme here, and a quote that I particularly like, which is popularly attributed to this guy named David Wheeler, is that all problems in computer science can be solved by adding another level of indirection. And in a way, that's sort of one of the big things that we are doing with Dali. So the starting point for the Dataset API is to say that instead of basically identifying a data set by an HDFS path and a schema and a partitioning scheme and embedding all of this information in every script that exists at LinkedIn, we actually want to separate that data out into a separate service. So we want to have a logical data set name or a table and have that map behind the scenes to an HDFS location, the storage format, the schema, partitioning scheme, indexes, statistics, all of the secondary information. And folks who are familiar with things like Hive probably recognize this. If you're familiar with data frames, you probably recognize this idea. If you've used a database, you probably recognize this idea. And that's fundamentally, what's at play here. And in fact, to build this, we're reusing a lot of that infrastructure. We're using the Metastore as the backend metadata repository. And after getting this going, sort of making this, this data set abstraction accessible to other components in the platform, we started to realize that while tables are great, there are some things that we could actually do better and some things that tables alone don't really satisfy. So we saw cases where people were actually creating or materializing 2 copies of the data. The data was the same. The only difference was that one copy was a flattened version, one copy was a nested version. And this might seem pretty mundane, but if you look at tools like Pig and Hive, the semantics in those components for accessing nested data are not very convenient. So just as sort of a productivity thing for analysts, it became necessary to create these flattened versions. We have one data set, something called the identity superblock, which is a data set basically with all of the information about particular users or members on the site. And the ISB superblock has 8 levels of nesting. So using Pig or Hive, that's terribly inconvenient to use. Another interesting use case is sort of multiplexing and demultiplexing data sets or event types. So we have another sort of like big monster data set called page view events, which is basically the clickstream information from the site. And PVE is actually a union of hundreds of different event types. If you look at most of the queries, 99% of the queries or workflows that people are running against PVE, they are right up front filtering on one or a handful of specific event types, and they're typically filtering out, let's say, 80 or 90% of the events in this data set. And yet they have to scan through the entire thing. So it's very inefficient. On the other hand, though, you have a lot of workflows that just sort of, let's say, massage the records in PVE as they move the records from one place to another, maybe applying a slight transformation or something like that. And if we were to demultiplex page view events into separate event types, it'd be very inefficient for them to sort of manage this. Every time someone added a new event type, they would have to go and update the workflow in order to account for that and make sure that it's added to the pipeline. We also see cases where people need to patch bad data or where they need to or want to make a backward incompatible change. And right now, there are lots of sort of backward incompatible changes that aren't possible. Things like removing a field from a schema, narrowing the type of an existing field. And finally, another, I think, big thing that we want to be able to support more of is code reuse. I think one thing about Hadoop that is maybe not appreciated enough is that Hadoop really opens the door for amazing new ways of creating really bad technical debt. I think Hadoop is almost like the collateralized debt obligation, right, of the tech debt world. You can run up an amazing debt without knowing it. 2 years down the road, you realize how screwed you are, and it takes years to back out. And a large part of this is that it doesn't sort of facilitate easy code reuse. So you see a lot of people copying and pasting references to blocks of code from one Pig or Hive script to another. You see people passing jar files back and forth over Dropbox without declaring their dependencies. And you have a lot of workflow management systems, Uzi, Azkaban, where people are able to upload basically bags of binary artifacts. And in the worst case, to me, right, this just represents kind of like a bag of garbage. I have no idea where it came from. It works great for a year. Suddenly it breaks. Who knows why? And at that point, it's hard to even figure out where the code came from. So what we really want to do is find a way of decoupling the API of a data set from the implementation details of a data set. We want to give the data producers more control over managing that API and evolving it in a safe manner. And coupled with that really is the goal of providing tooling and a process that allows people to manage this whole thing easily. So if you've worked with databases before, you've probably heard of views. With Oracle or MySQL or Postgres, the idea fundamentally is that you have something that looks like a table, but it's actually defined in terms of a SQL query which references other tables or views. So you could think of it as something that looks like a table, but it's actually a function. in most traditional databases, most views are typically materialized, right? So you materialize the view, the data gets written out to disk. Hive is interesting in the sense that views are all virtual. So every time you select from a view definition, behind the scenes, Hive is rewriting the view query. And if you have a view defined in terms of a view, defined in terms of a view, it basically gets rewritten as a nested subselect, submitted to the optimizer. The optimizer is able to do a global optimization, come up with hopefully an efficient query plan, and execute that for you. So we wanted to basically free the view. We wanted to take this great idea that Hive borrowed from conventional databases, and then we wanted to make that accessible to the other components in the system. And to do that, we made a couple of changes. So one thing is we figured out a way of embedding Hive's query compiler and execution engine inside of these data adapters, which work with Pig and Spark and Scalding and things like that. We also added a couple of additional restrictions on top of what's possible with Hive. So in these views, which we call Dali views, we only allow projections, filters. We don't allow big table joins. We allow map side joins if you can express them in a UDF. The motivation for doing this is sort of twofold. So one thing is we want people to be able to evaluate these views within a single process. We don't want it to require a reduce phase. And similarly, since these are virtual views, we don't want people repeating the same expensive join or aggregation operation over and over and over again. We have eventual plans to support pre-materialization for views, and at that point, we're going to add support, or I guess remove the restriction on not allowing joins and aggregations. But for the time being, this is in place, and people are getting quite a bit of benefit out of it. Another feature that we added to Pig and Hive is the ability to declare dependencies on UDFs and have these resolved from something like Artifactory using conventional sort of declarative dependency resolution. This particular example shows how we were able to solve that problem of providing a nested and flattened view of the same data set without creating two different copies, just by creating a flattened view on top of the original nested data set. And this is an example of reading one of these Dali views from within Pig. That's also another feature that we added to Pig and got committed upstream, the ability to basically reference a dependency on a jar file and have that resolved at runtime. So versioning, I think, is a pretty interesting topic. One thing, of course, that I think versioning allows is the ability to do incremental upgrades. And when you have a couple hundred people who are trying to collaborate on a complicated data pipeline, when you have nested dependencies and fairly complicated graph of dependencies between different phases in the pipeline, you don't want to be required basically to do a force push which simultaneously upgrades everyone, because that really raises the stakes. You have to be right, because if you're wrong, you're going to break everyone instantaneously. So by providing a mechanism that allows us to version views and actually publish multiple versions of the same view at a time, we're giving people the ability to incrementally upgrade. So it lowers really the liability on you in the sense that you can publish something and you're going to do testing to, as best as you can, make sure that it's correct. But if it has a bug in it, you're definitely not going to break everyone at the same time. And hopefully, as people sort of incrementally upgrade, you have a way of getting some signal and feedback about whether what you published was a good version or a bad version. So another interesting thing I think that we've done is to leverage some of the existing patterns out there for managing views. So if you look at sort of the database community, if you look at what DBAs are doing over the last couple of years, it seems like it's gotten a lot more popular to check your SQL queries into Git, to version your schema evolution scripts and things like that. With views, we're trying to make it more popular to think of your views really as software artifacts and try to bring some professionalism really to the data analysis side. of the engineering culture at LinkedIn. We're also able to take advantage of some of the nice infrastructure that's already exists at LinkedIn for building software systems. One thing that we have to worry about really is how to manage the namespace. SQL provides really a 3-level namespace: catalog, database name, view or table name. And it's easy for that to get crowded pretty quickly. The approach that we've used here is just to map the DB and view name to the group ID and artifact ID of the artifact that we're publishing. So I think in terms of engineering, like, I'm okay at writing code. I'm okay at designing systems. I know that I'm really bad at defining processes. I'm really bad at running working groups, writing emails, trying to get a bunch of people to agree on something. And I think sort of a hack, if you will, that I took advantage of here was really leveraging a process that already exists at LinkedIn. So there's a team of about 100 people who are responsible for the tools infrastructure at LinkedIn. What we really wanted to do was provide a way for people to negotiate contracts between consumers and producers. And what are some examples of contracts? Well, schemas, right? Physical schemas provide one type of contract, but in practice we've seen that that contract isn't good enough. You're able to say that something is a string, but what you really like to say is that it's a URI or enumeration. There's no way in general of saying across the board that constraints like nullability exist. We've seen a lot of cases of these sort of like fire drills, right? Where because of vagueness or questions about the meaning, really the semantic meaning of a field in a schema, a metric plummets, a change to a pipeline gets made, and it takes a week to figure out what happened. A good example of this that I saw recently, we have a data set which contains 2 different time fields. The old time field was deprecated but never actually removed. New time field was added. One of them is in seconds, the other one is in milliseconds, but there's no annotation or way of actually communicating this. So at some point, someone updated a script to point to the new field without taking that into account, and it led to a change which was visible all the way up to the CEO. Took several days to figure this out. And the question is, how do you actually communicate this to the people who are consuming the data set? So we basically want a way of defining contracts and of evolving contracts. I think it's worth thinking about like what makes a good contract. Contracts should be easy to find, they should be easy to understand, and they should be easy to change. Contracts that don't satisfy these conditions are really good for lawyers because they lead to lots of billable hours, but I don't employ any lawyers, so it's not really an interest of ours. So like I mentioned earlier, we were able to sort of hijack an existing process. And the process that I'm talking about is how people at LinkedIn right now develop software. And it's a process that I think a lot of you will probably recognize. So how do you change software? Well, typically you check out a Git repository, you prepare a patch, you submit a review request in the form of a pull request or review board. The people who own the ACL on that repository will review it. If they like it, it looks good, they'll accept your pull request and it becomes part of the code base going forward. How would you evolve a contract, though, that is owned by the data producer? Well, we can leverage a similar mechanism. As long as we have a way of expressing that contract in terms of logical constraints, and if those logical constraints live in the repository where the view is defined, a consumer who then looks at that contract and thinks, well, I've observed that this contract could be refined, that this type could be narrowed, or I want to define a constraint linking this field and this other field on a per record basis. If you want that to get added to the contract and you want what is up to this point an assumption to actually be part of the written law going forward, you have the option now of submitting a review request to the view owner. The view owner accepts it, it becomes part of the contract. the view owner bumps the version number, which is a signal to other consumers that something has changed. On the other hand, if the pull request is rejected, the consumer still has the option of adding it to another repository and running this check on a daily basis to see if at some point their assumption is no longer valid. So I think there are two interesting aspects of this, because the contract really serves two purposes. It provides really a constraint-based testing mechanism, a set of logical constraints that we can evaluate on a daily basis against real data. And that sort of solves the challenge of how do you test something like a view, because it's heavily dependent on real data. Unit testing for a view is, I mean, you can write unit tests for it, but I don't think it really serves much purpose or provides much benefit. The other thing is that these logical constraints are also really data quality tests, things that you can deploy and monitor, and if they change, you know that the contract is no longer valid and that something needs to be fixed. So let's see, in summary, really the goal here is to make things more predictable for the data consumers, to reduce the level of entropy, and sort of acknowledge that things are constantly changing and that we need a system and abstraction that takes that into account and allows people to manage it in a low-friction way. And from the standpoint of producers, we want producers to know what lies on the other side and to be able to make changes without having a lot of anxiety about what's going to break. And from the standpoint of infrastructure providers, myself included, we want to really open up the freedom to optimize how the back end works, take advantage of the new things that are coming out, and put ourselves in a better position to get to a place where we're able to really make multiple clusters look like one cluster and do global optimizations across all of that back-end infrastructure. And the goal really then is to move from this sort of cloud of indecision and confusion to a model where it's very easy to figure out with a global understanding what's happening behind the scenes. So if you want to get in contact with me, here's my contact information, and opening it up to questions if you have any. Yes?
So 10,000 nodes, what does your kind of DevOps or operations team look like in terms of rough size and scale?
I think we have about 5 people on the ops team right now. And they're part of a much larger SRE organization at LinkedIn. So right now, the size of the development team is actually like a multiple of the size of the ops team. Yep. Any other questions? Yes?
How do you integrate with schema registry, for instance?
I'm sorry, the question is? Right, so that's a good question. The question is, how do we integrate with schema registries? So we're actually in the process of trying to consolidate the schema registries at LinkedIn. Up until the introduction of Dali, there really wasn't a schema registry for the offline side. For the online side, we have a Git repository which stores all of the Avro schemas for tracking events. If you want to publish new data to Kafka, you have to go through this process of getting your schema added to this repository. I think over time, people have realized that it's not really a good idea to store every tracking topic schema in the same repository. There are hundreds of schemas there. It makes it hard to monitor the repository for changes to only the schemas that you care about. And similarly, there are really connections between these tracking topic schemas and then the corresponding schemas that we see in systems like Espresso, which is a document store at LinkedIn, as well as the corresponding schemas in the offline side. So another project that we're working on related to Dali is some tooling, Gradle plugins basically, which allow you to create a repository which represents a data set, which has the schema for the Kafka tracking topic, along with associated Espresso schemas, your view, which wraps all of this information on the offline side, and tooling which, given the tracking topic schema, will actually auto-generate these other schemas for you. And as the tracking topic schema changes, auto-evolve the corresponding schemas and views that are connected to it. Any other questions? Yes? At the moment, no. But Atlas is something that we've been looking at closely, and I think over the next couple of months, we'll probably have a better plan about that. Any other questions? Yes?
Do you combine the Dali technology with traditional relational databases?
At the time, right now, we don't. But I think that's one of the things that we're interested in doing in the future. So I mentioned earlier that a lot of the stuff that we've built so far is actually built on top of different components of Hive. And I like Hive a lot, but I also want to sort of say that I view Hive as more of a temporary implementation detail than something that we're going to be tied to long term. And I think that depending on what happens with Hive, what happens with the other SQL and Hadoop storage engines, we may find ourselves switching to something else. It's hard to make a bet about which one of these SQL and Hadoop layers is going to survive. I think the only safe bet is to say that SQL is a safe bet or the right thing to depend on. Yep. Any other questions? Yep.
How does this 10,000 node cluster integrate with your search possibilities?
So we don't have a 10,000 node cluster. Our largest cluster is 3,500 nodes. Yeah, but how does it integrate? Well, search is provided by online services, but the search indexes are actually generated in Hadoop. And then through different pipelines, we manage to get those over to the online side.
Are you using Solar then?
At the moment, I don't think we are. I think probably not the right person to answer that question. But I could put you in touch with the people who are. Any other questions? Yes?
Any plans to open source?
The question is if we have any plans to open source. We definitely want to open source this. I think one thing that's pretty cool about LinkedIn is it's very easy to open source things at LinkedIn. There's a very strong culture of doing that. And there are a lot of examples of things that people have open sourced which have become very popular projects. I think one thing that's going to make it hard for us to open source Dali is that a lot of the value actually derives from the fact that we're trying to tightly integrate it with the rest of LinkedIn's tooling and software development infrastructure. There are components of it, though, that I think we can open source, including the support for views. And there's things that we've already pushed upstream, like the ability to declare dependencies on UEF artifacts and things like that. But my goal is to get a lot more components of Dali open sourced within the next 1 to 2 quarters. Any other questions? Okay, well, thanks.